I'm going to talk to you about interactive analytics in human time. This is the same talk which we presented 2-3 weeks back in Hadoop Meetup. I'm trying to get into the details of what we try to do at Yahoo and how we try to achieve the results. And lastly, we'll also talk about a few restaurants. So interactive, the most important part is what does interactive mean? How do we see interactive? What is interactive in the sense of Yahoo's interactive analytics problem? So for example, there's 60 billion events. This is from one of our production data sets. It's one of our benchmarks. The data set has 60 billion events. That's close to 3.5 terabytes of compressed data. And when we are doing a group by with an order by, that is almost like a full scan, the total response time is around 400 milliseconds. So that's one example of what is meant by interactive. Another example is the application interactivity. So me and Sunil, when we did all this work, we represented the ad systems. So in advertising, there's a notion of an application interactivity. If you come and book an ad, how quickly can you actually serve the ad? So that is also a notion of interactivity. So in our problem statement, we wanted the serve to insight latency to be less than 2 seconds. So to summarize this, there are two aspects of what we call interactivity. One is, given the data, how quickly can you query on it? The second is, how quickly can you actually ingest the data and make a query on it? So both of this is in the definition of interactivity. Moving on, the agenda for this talk will be based on the following 5 items. We quickly go through the motivation to discuss what is the problem. We'll then look at our approach, how we approach the problem. We'll do a problem deep dive on a specific problem which is called instant overlap. And lastly, we'll summarize our findings and then take questions. So one of the common motivation problems that all of us have in this field is that there is lots of data. Lots of data is a very relative term. So at least in our context, lots of data actually means that every day you are dealing with billions of events. In this example that I've taken, it's around 30 billion advertising events which are meaningful to us a day. And that translates to tens of terabytes of compressed data. So that is what we define lots of data as. It's a very relative term, so it varies from company to company, use case to another. On the same data set, you want to deal with insights which deal with minutes to year grain. So somebody might say, show me the total number of impressions in the past 10 minutes, whereas another analyst might have a question saying, how are these impressions varying over the past 1 year or past 3 years? So the grain of data varies across a wide range of time frames. The total retention, just like in being any major public company, we deal with multi-quarter retention of data. Lastly, the notion of aging needs to be factored in. So you need to have data aging factored in. That is, data that is closer to the current time is more important than data that is probably 6 years old or 3 years old, which can probably take more time to do. The next big problem that we wanted to solve is a wide variety of analytics. Analytics is a broader term that is used. One of the basic means of analytics is just plain reporting metrics. You have a set of dimensions, you have a set of metrics. You just count the metrics on a dimension and display it on a UI. Typical reporting use cases. However, if you go a level deeper into advertising, you'll realize you need to do attribution. You need to attribute either clicks to impressions or conversions back to impressions. Or you want to attribute the person who saw the ad back to the ad's features. So there's a lot of stuff that happens around attribution. If I describe myself in a dimensional word, I would just say my name is Supreet, I work in data, I'm currently standing in Yahoo. These are all my dimensions. However, in advertising, nothing is as simple as a few dimensions. It's hierarchical, it is multi-dimensional, a lot of nested structures. So we want to provide analytics in all of these aspects. I'll briefly get into building and targeting optimization later, but at a very high level, since Yahoo is big into ad targeting, There are a lot of analytics which rely on optimizing the right ads to the right users, and we need to build algorithms, and this also deals with a lot of data about the user. How many of you have heard about, hey, I want to know what is the unique number of users in any given application? I guess aware of the unique user problem? Nobody? A few nods. So unique user problem is a very different problem compared to additive metrics. So it's not about adding the number of impressions or adding the page views. Unique user typically means you have to go back to the raw data set and recount it. We will touch upon this problem in more detail. So to summarize this, we have to deal with analytics which are specialized, which are more generic, which are very basic to spanning multiple dimensional data structures. So analytics is a big motivation to solve the problem in practice. This is a very high-level generalization of a very common design pattern. It has been presented in multiple user groups and summits. So in a typical data processing scenario, you would have a data producer which produces data. Examples are websites which send beacons, ad serving system which log events, users who come onto systems and generate data, or in case of social media, people posting. All these are examples of data production. Now once data is produced, typically have two ways of accessing data. One of them is using a real-time part. One is a real-time path where you typically are processing data close to real-time or very low latency. The second path is a slightly high latency path where you are taking more time to process the data. Irrespective of whether it is real-time or the high latency path, the end customer doesn't really care about how you process the data. He's just caring about insights and analytics that could happen in real time. At Yahoo, this has been a major problem for multiple reasons. One is there are systems that just do this on the real time or process the data on the batch, but restating the data or just reconciling the data with concerns about atomicity, how do we actually show back the metrics that are already stated to the customer, all that is a big problem. So we wanted to deal with this also as a motivation for our interactive. The last aspect, which is like the basic theme of why we are doing a lot of things, is that we wanted to do all of this in human time. So the way we define human time is that 99 percentile of our query should return less than a second. There are very strong voices which say it should be less than 500 milliseconds, but less than a second kind of is fine as a tool. On the default time frame, which is the default page load, the data response should be less than 300 milliseconds. So this is what we confine or quantify human time. I'm going to talk about a problem called instant overlap, where for that problem space, the response time needs to be less than 3. I just wanted to mention that as well. And lastly, data ingestion to when the insights become available needs to be less than 2 seconds. Anything more than 2 seconds is not wow. So to summarize the motivation, there's lots of data that we all have to deal with. Analytics from generalized reporting analytics to specific analytics. Data restatement which happens due to processing in real time and batch. And lastly, doing all this within the bounds of human. So now we go to the next section of the talk, where we talk about our approach of how we wanted to solve this problem. So this is a typical data stack. It's a logical view of any typical data application. So in any data application, you would have a set of functions which are together combined as ingestion or collection. There are a lot of examples for this. The whole purpose of this, these two boxes would be to ingest data or to collect data from any producing system. Then on the raw data set that is ingested, we apply very basic transformations, maybe filtering, cleaning up some data, which are called aggregations or transformations. The aggregations here are not very heavy but are very, very basic. these are just helping to clean up the data to further load it into tools which help you query data. The next section is broadly termed as a data warehouse. And this is where we spent a lot of time in the past 6 to 8 months to optimize and get the right architecture and the right implementation. So in the data warehouse space, we are looking at persisting the data that comes out of all of the ETLs, runtime compute, what is the right kind of caching to be built, the right APIs to expose the data, and lastly, if the entire API is dealing with SQL, you want a way to translate SQL to something that the UI can understand, which in very generic terms is termed as a middleware. So if you look at this logical stack, the very next question that we wanted to answer is, what are the characteristics that are important for Yahoo when we look at this stack? Yahoo has invested heavily into Hadoop because Yahoo kind of open source Hadoop is doing the pioneer, it's a pioneer for Hadoop. So being compatible with HDFS, aligning to the principles of batch processing which is Hadoop based becomes very, very important for us to pick any data stack. So on the ingestion and the pipeline layer, having an ability to do batch processing, real-time processing, all the notions of late data arrival processing, how do you do monitoring, how do you do anonymization, all this becomes important. On the persistence, compatibility with Hadoop, along with performance aspects, maybe dealing with columnar data, compressed serialized bytes, or dealing with flexibility with respect to schema evolution, all of those become very important in our evaluation. On the caching aspect, a very high-level view of picking a caching solution is whether the caching is inherently distributed or is it standalone. That's a very kind of a binary view. It helps you take off a lot of solutions off the table. Another way of looking at it is we are able to cache objects versus cache the results. So that gives you more flexibility when you deal with multiple grains of data or the same data being viewed through different dimensions. With respect to access, SQL is such a intuitive paradigm these days that you can't move off SQL. So we wanted to stick to SQL-like access request. And lastly, translation from SQL was an optional aspect. So having looked at the characteristics, let's look at the choices that are there. So on the pipeline, the choices are pretty standard, and I think this is going to many companies in the valley. We use Hadoop. We have developed an entire pipeline stack on Hadoop, which relies heavily on PIP and Uzi. And for stream processing, mostly topologies in real time, we use Storm. We are able to use Trident at a very large scale, but Yahoo's implementation of Storm runs on Yarn and it has all the nice propagation we can expect of Trident also. On the runtime compute, this space is quite busy. So we have traditionally tried a lot of data applications using Oracle, and Oracle or MySQL doesn't really scale up because it's kind of standalone SQL systems, and there's always the problem of how flexible they get when you deal with multiple dimensions, multiple time frames. You always have to build three applications. Often we have also tried HBase. But the way we use HBase, you need to translate any problem to a lookup problem, which kind of takes away the fun of flexibility. So in the moment you add a new dimension, you have this whole bunch of jobs on the grid which has to compute for the same aggregates. We did a benchmark of Shark, Impala, and Hive. And Shark in our benchmark was faster than Impala. But this benchmark was dated in October 2013, so a lot of things might have changed now. However, between Hive and Shark, we went with Hive. The biggest reason why we went with Hive is Yahoo has heavily invested in Hive. That alone can't be the reason. But more importantly, Hive is very well supported and it scales up with larger data sets better compared to Shark. So Shark is very performant when we deal with smaller data sets. But the moment we started getting terabytes of data with huge performance constraints, Hive was very stable. So Hive at least was there. And for all real-time analytics and interactive analytics, we went with Druid. Druid is an open source project which is driven by MetaMarkets, and it has some of the nice properties of being a columnar store, having bitmap indices, and it supports a compute engine which performs very well for kind of use cases that we wanted to do. On the caching, we use Memcache. Though Memcache is standalone, as a client we can make it distributed, so we handle the distribution part. We didn't spend much time with Redis, though it was an option because our data structures were pretty simple. We didn't want to spend a lot of time. And on API, it was a standard JSON REST API with JDBC, ODBC being supported out of the box on top of Hive. So after a lot of evaluations, the bolded items were what we picked in our stack. Now that we looked at the criteria, how do we actually wire it up? So typically there are data producers. I've listed a few systems here, but depending on the domain that you operate, this might vary. All of this data is fed into two paths. One is a batch compute path on Hadoop, and the other is a real-time path, which is a Storm topology, which is also being run on Hadoop. Once the data comes out of Hadoop or Storm, it is persisted, and Storm we directly hook it up to Druid. So the reason why we built this Storm to Druid connection is that we wanted the data to be variable while the indices were built. So it's a notion of making mutable indices variable. And the same data exists on both Hive and Druid. So the numbers will always match in all our interfaces. And lastly, there are customers who build dashboards to applications to work on our problems. This is a very high-level view of our approach to the same problem that we took. So how do we actually attain the notion of human time, as we define it in the motivation? We use Druid for interactive queries. For the quick ingestion, we use Storm to Druid. We kind of push from Storm to Druid rather than typically doing a pull out of the message queue. So we don't have a message queue in between, but we can certainly experiment with message queue with the time like this. And we do specialized computation for future processing, mainly supporting the approximate computation status or feature sequence-based overlap, which I talk about in more detail very soon, or doing some custom indices and custom data structures into it. So with the stack that was described here, we are able to achieve the notion of human time as we described in the motivation using these high-level principles. So with that, we get to the next section of the talk. So this talk I presented mostly as a data science talk. So I'll speak a lot more about the actual problem that we were trying to solve. And in the end, we can take questions on both aspects, maybe the infrastructure, architecture, all that. So a typical view of users, right? Users in the world can typically be looked at as sets of people. A very simple way of looking at sets of people is, let's look at all the people who came to Hadoop user group in their own car. So that can become a set of people in the same group. Now we can take another set of people who are interested in following FIFA. And needless to say, there's an overlap between the two sets. It's a very simplistic view of looking at sets of people. And there's veggie pizza here, so there will always be another set of people who only care about vegetarian stuff. So that's the third set of people. Now if you look at a simple metric saying how many people qualify in each of the sets, so that becomes the area under the curve, or under the circle in this case, the number of people who belong to this set. As we take two sets, it should be obvious that there is an overlap between the two sets. So we just cannot add up the car commuters and soccer fans and say this is together making up one. It's a basic problem of set intersection. And as the number of sets increases, the overlap and computing this overlap in real time is going to become very tricky. One big takeaway from this slide is that computing overlaps and computing unique user across sets is a non-additive problem. You just cannot add it. It's always non-additive. So how do we generalize the problem? The problem is, of course, non-additive. If you do a very naive approach, you need access to raw data. Without scanning through all the raw data, there is not an easy way to solve the overlap problem. But in our case, the raw data means you are scanning millions of events a day with multi-quarter retention, and that translates to terabytes of data. So that again is a large-scale problem. And the same overlap problem can be looked at as a 1:1, a 1:1, and a few is 1. So let's get into each one of this with an example. So between car commuter and vegetarian, you can find an overlap. This is an example of a 1:1 overlap. You are taking two sets of people and saying how many people are common between the two sets. In the 1:N overlap, for the car commuter set, you are trying to find the top sets which have a higher overlap in the same set, which is car commuter. And in the few-is-to-N problem, you are combining the left-hand side with more than one set. You are saying, for all car commuters who are vegetarians, how can I find a top overlap? So you can approach the problem as a non-additive problem, which is of course a non-additive problem, but also view the same problem space into three different angles: a 1:1, a 1:N, and a few-is-to-N. So restating the problem motivation with respect to instant overlap. So given two sets, how can you identify exact overlaps in close to real time, with the constraint being that the data set that we are trying to scan is spanning multiple millions of events and lots of terabytes per day with not many quarter events. And for those of you who want to understand this in a set notation, it is just a simple AND operation or intersection that we are trying to do. What about existing approaches? So this field has been researched a lot in the past few years. So there are a lot of existing approaches. One naive and interesting approach is to just do exact compute paradigms, that is use joins. So PID, Hive or any other framework which runs on Hadoop supports joins. So you can actually do joins. They are of course exact, but the biggest problem is they are never real time. So if you typically do a join for a 1:N or a few-is-to-N overlap, at least on Yahoo's data, where we have close to 630 million unique sets. So in the example that I gave, there were 3 sets. In Yahoo's data, we can actually characterize the data set to 630 million combination unique sets. Now when you have to do a 1:N on that, the job takes multiple assets. Never going to be such a simple join. The other level research technique in the industry is to use approximate algorithm. One very popular algorithm is the hyperunique sketch, which is from Google. And Yahoo has also invested heavily into another sketch algorithm from KMU. Approximate algorithms try to represent a set of users and try to give you functions on top, maybe to merge the same hashes or to do something more on top. But the largest problem is it needs a lot of tuning to get the right accuracy for the size. And needless to say, it will be close to real time but never exact. To get an exact intersection across multiple sets is not a bounded deterministic problem. So how did we want to tackle the problem? So we kind of took an incremental approach. We looked at some of the approaches that the approximate algorithms have taken. We looked at some of the data sets that have been created. And we kind of introduced 2 new data structures. That is what we call. So the first part of our approach, we do feature sequence encoding. So let's take an example of 3 users in this room: Ram, Tom, and Sam. And Ram is a car commuter and a soccer fan. Tom is a soccer fan and a vegetarian. And Sam is all of the 3. So we encode each one of the users into these feature sequences. Once we encode each one of the users into the feature sequences, we then eliminate the user. At this point, we only care about the feature sequences. We don't really care about whether it was Ram or Sam or Tom. So So for some of you it should be obvious that at this point the total number of unique users in the system is an additive metric. So if I just count up these values, the total number of users become additive because we have made a feature sequence encoded data set. After we do the encoding, we represent these low qualifications into a bitmap. So if you take a car computer, which was present for Ram and Tom, which is user number 1 and 3, we would just encode that as a bitmap where we set only the bits where the user is coming in the feature sequence. And once we encode it into bits, we represent this entire bit set into a compressed bitmap. So that is the second data. So to summarize the two data structures, one is we keep a feature sequence with a count, where the feature sequence and value of the count makes the entire non-additive problem the additive problem. And the second part, we take the feature to no qualification and put it into a compressed bitmap. Once it is represented as a compressed bitmap, there are compression algorithms on bitmaps, and Druid uses a compression algorithm called concise, which makes the compressed bitmaps bitwise operators are allowed on it. Which means now to find all the rows where car computer and the vegetarian existed, we just need to take the compressed bitmap for the sequence which has both of them and then do an AND on top of it. And then you get a number of rows. Once the number of rows are there, with the other data set which is keeping track of counts, the counts are additive, which means you can actually address this in close to real time. We kind of transform the non-additive overlap problem into a set of data structures which makes it additive and computable in data. So that was the one innovation. And lastly, we wanted other algorithms like approximate top and or doing loop bytes or any other metric that can be computed on Druid to work on the state problem. So we just look at the number and look at how we were doing the same problem. So 1:1 overlap on the grid currently takes around 19 hours. And for any fused one combination, it caused a total reprocess because we actually have to go back to the order. Whereas for instant overlap, we do reprocessing of building a custom index, those two data structures. And once it's loaded into memory, we can support all the combinations. And the worst, which is the fused one, is less than a minute. So that's the norm. So with this, I would like to summarize. What the solution that we built is called an advertising data warehouse. We are handling petabyte scale. That's the scale of data that we handle. We provide a normalized view across many systems. Provide specialized analytics with optimization and data structures built to solve that analytical problem. Address the data restatement problem. We kind of deal with both strong and large and do a metadata switch to address the data restatement. And lastly, do all of this in the context of real time, which was defined in the motivation. So with that, we can open up